Alright students, I wanted to give you a little tutorial video to go along with the homework solutions since we've lost some days due to snow days. We're looking at the stoichiometry practice page that you were given before our snow days, before we went into our stoichiometry lab. They all tend to be limiting and excess problems that follow a very similar pattern. I'll walk you through the 3 pages to this. Feel free to pause and look at the answers and look at the math as we go. One of the other things to note is that as you're looking at how I've written out my problems and how you've written out your problems, if you find that you aren't labeling things, your work, as much as I am, then you're shooting yourself in the foot a little bit. One of the big things we're allowed to do in IB chemistry is award points for error carried forward, meaning that if I can tell that you've made a math error or a procedural error on one step and then carried that solution on later to solve problems with, you won't be deducted points later on for using that wrong number. However, the only way I can do that is if you've labeled your work and I can tell where your error is. So please be certain that you are labeling everything excessively even as you solve these problems. The first thing to do will be to double check your balanced equation problems at the top of the page. This was just a short review section. Specifically pay attention to number 2. Once you've checked those, let's take a look at the questions that follow, starting with number 6. In problem number 6, we're given 2 starting amounts. We're given 35 grams of C6H10 and 45 grams of oxygen. It's tough to know which of those 2 to start with when we're trying to figure out how many grams of carbon dioxide can be formed. This is a typical limiting and excess problem. What this means is we'll have to solve for the grams of carbon dioxide formed 2 times, once with each starting value. Whichever one gives us the lesser amount will be giving us the correct amount. So if I take a look at the work here, we can see that I've started with 35.0 grams of C6H10. I converted that to moles using the periodic table and the molar mass. Using the balanced equation, there are 2 moles of C6H10 for every 12 CO2 that are produced. And then for every 1 mole of CO2, there are 44.01 grams of CO2 according to the periodic table and the molar mass values. And that would give us 112 grams of CO2. What that means is that if I used up all 35 grams of C6H10, I could produce 112 grams of CO2. We don't know that that actually happened though. So we're going to start the problem one more time. We're going to start it with our 45 grams of O2. We'll convert it to moles. Typically that's a good first step using the molar mass. We'll use the balanced equation in which there are 17 moles of oxygen consumed to produce 12 moles of CO2. And then for every 1 of those moles of CO2, there are still 44.01 grams of CO2. And if we do the math there, we find that 43.7 grams of CO2 can be produced. Meaning, if I use up all 45 grams of oxygen, I'll end with 43.7 grams of CO2. And once that happens, the reaction will stop. I won't have any more grams of oxygen to work with. I'll never be able to make the 112 grams in that case. So this 43.7 grams of CO2 is the actual amount that can be produced. That also means that oxygen, the one that I ran out of in producing that, is our limiting reagent or reactant. Question number 8 asks us how much of the excess reagent is left over after the reaction from problem 6 is finished. For that, I'm going to take my limiting amount of oxygen, and I'm going to solve for how many grams of C6H10 are needed. If we look at the work here, I trade grams to moles using the periodic table, and then for every 17 moles of O2 that are consumed, I will react 2 moles of C6H10 according to our balanced equation. And then for every 1 mole of C6H10, I'll have 82.16 grams according to our periodic table molar masses. In doing the math, that tells me that I'll need 13.59 grams of C6H10 in order to use up all of my oxygen. We're told in the problem that we have 35 grams of it. So if I take 35 grams of C6H10 minus the 13.6 grams, rounded for sig figs, that I need, I find that I have 21.4 grams excess. That means there is too much C6H10, which we already knew because we knew it was excess, and this tells us how much C6H10 there is left. The last part has to do with comparing what we can calculate, which is a theoretical yield, with what someone actually did in the lab. To do this work, we need percent yield. Someone actually went to the lab and they figured out that they could make 35.0 grams of CO2 experimentally. They did the work, they measured their product, and that's what they came up with. Now we've calculated we should be able to get 43.7 grams of CO2 in a perfect world. But you guys have seen how difficult it is to capture all of any product that's produced in the lab at this point. So you'll be able to see pretty clearly that there's a difference between the two of those, and that's not an unreasonable thing to find in a lab. If I take the actual amount divided by what we'd get in a perfect world, times 100, I get 80.1%, meaning that of what could be expected, of the 100% that we'd love to get, 80.1% was achieved. Now that process that we went through on those problems is what will follow on the next pages. On the next page, our first step is to make a balanced chemical equation using acetic acid and aluminum hydroxide. It's an acid and a base, and they react to produce water and a salt, aluminum acetate. There are a couple different ways of writing acetic acid. If you've got a different way of writing it out that you found in looking it up for this problem, don't panic. I wrote it in one method. There are a couple different ways to write it. As long as you've got the same number of carbons, hydrogens, and oxygens, you've probably got the same formula. And then I balanced it. It's one of those reactions where you have to balance it in order to have the right ratios. Question 11 is just like we did on the previous page. We've got two starting amounts, and we have to solve for one of our products using each of those two starting amounts. First, I did the work with the acetic acid, converted grams to moles, used my moles to mole ratio, and then figured out how many grams of product that would be per mole. And then I did it with the aluminum hydroxide. Same process, convert it to moles, use a mole-to-mole ratio from the balanced equation, and then convert moles of our product to grams of our product. And as you can see, one of the two gives me a significantly lower amount. 142 grams of aluminum acetate is what will be produced if we use up all 125 grams of our acetic acid. The other amount tells us what we could get if we used up all the aluminum hydroxide, but it's clear that we've run out of acetic acid long before we'll get up to that 719 grams. So the actual amount we can expect produced is 142 grams of aluminum acetate. That means that the acetic acid, the starting chemical that gave us our lower amount, was our limiting reagent. Question 13 then asks us how much of the excess reagent will be left over after the reaction is complete. So the solution to this one, I take my limiting amount of acetic acid, that's the amount that we'll actually use up, and I figured out how many grams of aluminum hydroxide would be needed to react with that. This is just like the other problems. Convert grams to moles, use a mole-to-mole ratio to trade moles of what we have for moles of what we're after, and then convert that to grams. And this tells us that if I want to use up all 125 grams of acetic acid, I'm going to need 54.1 grams of aluminum hydroxide. In the problem, we're told we have 275 grams of it available. So if I subtract what I need from that, I'll be able to determine how many grams of excess there are. That's how much will be left over after the reaction is complete. For the next section, we're going to follow the same process. We've got a balanced equation to work with, and it's another acid-base reaction, which is a neutralization reaction. This also is a double replacement reaction, as we remember from our Chem 1 class. We have two amounts of starting material. They're listed a little differently this time. One of them is a grams quantity, the calcium hydroxide that we've started with before. The other one is, sorry, I started talking out of my tail. Got a step ahead here. What I'm doing in problem number 2 is I'm figuring out how many moles of HCl will be needed in order to use up all of my calcium hydroxide. I take my calcium hydroxide, convert that to moles, and have a 1:2 ratio from the balanced equation, and that tells me how many moles of HCl I would need. Molarity is calculated by taking moles divided by cubic decimeters. If I rearrange that, I can figure out what volume I need if I have the number of moles and the molarity, which I happen to have. We just figured out the number of moles, and we have the molarity, and that gives us the volume. So this is the volume of HCl that we would need if the HCl has this concentration in order to react with 5 grams of calcium hydroxide. Now we're moving on to the limiting and excess problem. In problem number 3, we have 15 grams of calcium hydroxide, and I have a volume of a known concentration of HCl. And I want to know how much calcium chloride, one of the products, I can form. So first, I'm going to do what we've done on the other pages. I'll take my grams of calcium hydroxide, trade grams for moles. There's a 1:1 ratio according to our balanced equation, so I can trade moles of what I have for moles of what I need, and then figure out how many grams that 1 mole has using the periodic table. And that tells me that if I use up all 15 grams of calcium hydroxide, I will produce 22.5 grams of calcium chloride. Then I take my 75 milliliters, or 0.075 cubic decimeters, times my concentration of HCl to figure out how many moles of HCl that would be. And then for every 2 moles of HCl, I'll produce 1 mole of calcium chloride. That's according to our balanced reaction. And then I convert that to grams. And that tells me that I will produce 2.08 grams of calcium chloride, a much smaller amount than this one. So what I've done in this problem, is the same thing we did on the other pages. This one I started with grams, it was identical. The other one I had a different starting amount. So I had to convert it to moles, and then I could work from there to find how many grams of product are formed. That means that HCl is our limiting reactant, because that gave us our smaller amount of ending material. The next part is to find out how many grams of excess reagent will be left over. So I take my moles of HCl that I found from problem number 3, and for every 2 moles of HCl, there's 1 mole of calcium hydroxide. Use the periodic table, find the molar mass, and that tells me I will need 1.39 grams of calcium hydroxide in this reaction. We're told in problem number 3, however, that we have 15 grams of it. So if I take 15 grams minus my 1.39 grams, I'll get 13.6 grams of excess calcium hydroxide. That's how those problems work. If you didn't get the correct answers or the correct solutions, now that we've walked through the discussion of how to solve it, cover up your work that you've written down, try it again, and then watch the video and compare with those answers one more time.